Hello. In this lecture, we will talk about analysis and design as well as the load factor. So just to remind you, in an analysis procedure, what we do is normally determine the actual forces that a structure can carry. So in other words, we know the structure and we know the properties of the material. We know the size of the members. So then we can determine how much force, what would be the magnitude of the forces that the structure can carry. Or if the forces are given, we could then evaluate whether the structure can support these forces or not. Now, on the other hand, in a design procedure, our goal is to determine the member sizes, the economical member sizes in a structure such that the structure can safely carry the loads that are applied to it. So in other words, this time we have the structure, the geometry, we know the material properties, and we have to design, calculate, determine the size of the members in order that this structure will safely carry the loads that are applied to them. Now, the key word here is safely. So in order to achieve safety, when we perform design calculations, we have to also include the load factor. And as was explained in a previous lecture, the use of the load factor is necessary to ensure adequate safety for several reasons, like for example, exceeded loads or material properties that are less than what is assumed, or for example, design methods that tend to be unconservative. The load factor is greater than 1, typically ranging between values of 1 and 3, and is normally used by multiplying the specified loads by the magnitude of the load factor. So hence the specified loads will become factored loads after they are multiplied by the load factor. And because the design methodology, the design operations are the ones that need to have this safety, the additional safety included, then we use the load factor only for design. We do not use the load factor for analysis problems. So only in design problems we should multiply the specified loads by the load factor to obtain the factored loads and use them in design. Now let's see how we can conduct analysis and design problems, calculations for beam under flexure, under bending. So on the left hand side here, we will discuss about analysis, on the right hand side about design. And as you remember, I'm sure, the bending formula is sigma equals m over I times y. And of course, we are looking for the maximum stress ever in a beam. So we need to use the maximum moment along the beam times the maximum distance to the extreme fibers of the beam. So therefore, we can determine the maximum moment from this equation in terms of the yield stress, or for brittle materials in terms of the allowable stress, ultimate stress, or failure stress. And this is of course a property of the material. It is given for every material. Once we know the maximum moment, of course we can calculate the maximum loads that the beam can support. If the loads are given, then we can determine the maximum stress that is developed inside the beam, and then compare that maximum stress with the yield stress, or for brittle materials with the allowable, ultimate, or failure stress, in order to determine whether these stresses, which are properties of the material, are exceeded by the actual bending stress in the member due to the applied forces or not. So in the end, we will say, yes, the beam can or cannot support the loads applied to them. If you are dealing with roll sections versus custom sections, you can use the section modulus, which is equal to the second moment of area divided by y max, and values of the section modulus for roll sections are of course given in tables. Now, if we perform design for custom sections, we can solve for the ratio of the second moment of area by y max that is required, and that would be in terms of the maximum moment along the beam, factored moment, so multiplied by the load factor, and sigma yield for ductile materials, or the allowable, ultimate, or failure stress for brittle materials. And of course, again, these are properties of the material. For rolled sections, one can calculate instead for the section modulus that is required by calculating the same ratio between the factored load and the yield stress, or the allowable, ultimate, or failure stress. Then we can select a member that has a section modulus larger or equal to the required one, but having the least mass that still satisfies these above requirements. That would ensure that our section is economical, selected in an economical way. It's the lightest, or in other words, the cheapest section that we can select. Now, in these formulae, you can notice that the axis of bending is not indicated for the second moment of area. So always you have to determine which exactly is the axis of bending, whether it's the x-axis or the y-axis, and then use the above relationships for the corresponding axis. So this is very important to make sure that you include the correct axis of bending in your calculations. So thank you very much for watching this lecture, and I will see you at the next one.